welcome you to the PhD presentation, The Defense of Pablo Abehsera-Morell. You already can see the title here, Acoustic Rendering for Realistic Interactions in Mixed Realities. I would briefly like to introduce the jury, which is evaluating your work, asking questions, and writing reports about that. But maybe we start with the two supervisors. So this has been supervised by David Poequino and by Brian Katz. And thanks for doing all your works with supervising the thesis. And as reviewers, there are present Annika Neithardt from the Hochschule Mittweida, Bernhard Seber from the TU München, University of München, David Kearney, University of York, Silvan Argentieri, sorry for the pronunciation, who is professor at Sorbonne University, and myself, Christoph Perschmann, who is professor at the Technische Hochschule in Cologne, Germany. I would like to say a very few words about what we experience in the next 2 hours, about roughly 2 hours. First, we will start with the presentation of the thesis, about 40 minutes, presented by Pablo. And after that, probably we'll have a short break, 5-10 minutes, and then we will continue with asking questions from the jury, from the supervisors, later on some short statements. But first, we start with the presentation. Thank you very much to all of you for being here, for listening to the presentation, and I hope we are ready to start. And I'm very looking forward to your presentation.
Okay. Thank you very much, Christoph, for that very nice introduction. I would like to start by thanking everybody who's here. We're going to have a look at the last 3 years of my work. So let's get to it. I'd like to begin by acknowledging some of the source of my funding. So that's the Sonicom European project, which has explored across different universities and startups, audio and acoustics for interactions in virtual and augmented realities. And here's a nice little picture of one of the annual meetings that we had, which happened in the same room. So what's the context behind my work? Well, as you may have guessed, it's around mixed realities. So as of late, we've seen the development and the release of many devices that allow us to experience mixed reality. This opens a wide range of use and applications, such as remote collaboration, training, simulation, education, and others. What it lets us do is interact with other people when we're not in the same physical space. So let's take, for example, this situation here. We have this person in a room, and we have a virtually rendered user who is in another physical room, and yet they are interacting. They can see each other, and they can hear each other, and they can have a conversation. So what my work is concerned with is what is the impact of the acoustic rendering on how their interaction happens. How good do the acoustics need to be for the interaction to be natural? Now, when we think about extended reality, we can sort of see it as a spectrum where on one side we have a virtual reality where all of the elements are virtualized. So the importance of the acoustics may be a bit lower. And this is because we are comparing the acoustics to our inner reference. So we can use paradigms such as judging plausibility. Whereas in this example that we have here, we have a virtual source that actually interacts with a real space. So the rendering of this person here will actually be compared to other sounds that are happening in the same space. For example, the voice of our local user or any other sounds happening at the same time. And so being a different kind of scenario, so we see changes in the paradigms that we use for assessing the relevance of the acoustic rendering. Now, the point of this slide is to show that there are many things that we could consider from the acoustic rendering and investigate to then see what their impact is on the resulting interactions. Now, there's many different things. typically in room acoustics, when we think of a configuration, we think of three main points. We have the source, so in this case that would be a person who's talking. We have the environment, that's the acoustic space, so the room, and we have the receiver or the listener. Now, for each of these three aspects, let's say, there are many things that can change and that can impact the final result. And that's kind of an overarching theme. We have the rendering, where in itself there are many things that can impact the final result. And so here I've highlighted a couple of the things that I've looked into that we'll be exploring in the next 40 minutes. All right, a quick overview of what we're going to look at. During my thesis, I've conducted 4 main studies, which I've chosen to present going from most fundamental to most applied. They're all relevant for the topic of acoustics for mixed realities. But let's say that they probe the problem at different levels of how applied or fundamental there are. So we start by looking at some measurements of voice directivity in the horizontal plane. We'll then look at a method for projecting directivity in reverberant conditions. Then we'll see what the impact of different directivity renderings is on how natural the scene is perceived. And finally, a more applied study where we look at how the mismatch between the acoustics for 2 people conversing in mixed reality impact how their interaction goes. So without further ado, let's go into the first study. We're going to refer back to this scenario during the presentation so that we can see the relevance of each study to the actual case. So what we're concerned here is we have this person who is talking to our local user, and this person may turn around at some points. And so this must be taken into account in the acoustic rendering. That's where directivity comes in. And so this study is about the characterization of that so that we can apply this directivity into our rendering pipeline. So when we talk about directivity, we talk about how a source radiates energy across directions as a function of frequency. A source that is notably directional is the human voice. The most obvious case being if I'm speaking to you, I'm not going to sound the same as if I turn away from you. I'm going to sound a bit quieter. Now that's a very generalized way of putting it, but it's a bit more complex because it depends on frequency. So here what I show are some results from Leishman and colleagues' work from 2021, where they measured the directivity of the human voice for running speech, so that's sentences in English. And what we see generally is that as the frequency increases, so does the directionality of the voice. Now this is relevant because seeing such differences can then impact in reverberant conditions. This can cause perceptual differences that may or may not be important to actually implement an auralisation. Now, of course, there are a couple, or more than a couple, there are several studies that suggest that it is relevant to include this phenomenon in auralisation, works such as that of Postman colleagues and Blau and colleagues. So in terms of the research questions for this study is motivated by the fact that the literature shows that different phonemes show different directivity patterns, and different languages contain different phonemes in different proportions. This leads us to ask the question then, if we take averaged speech, running speech for different languages, does the average directivity then change due to having those different phonemes, different proportions? As a second question, we ask if the sex of the talker could also have an impact on the average directivity of running speech, notably due to male and female voices having differences in things such as fundamental frequency and harmonic structure. This was also motivated by the fact that we had a high-resolution system available in the lab, coming from work from another team, that allowed us to construct a high-resolution microphone array for measuring, in this case, voice directivity. The motivation behind that being, if we test a finer resolution than what the literature shows, we could maybe reveal some relevant new information compared to what the literature already shows. So here's a picture of what the array looked like. It consisted of a metal arch with a diameter of 3 meters, where we would place the participant in the middle. They were placed in the middle with a calibration using 2 lasers and a camera system. And then once they were well placed in the middle, we got them to read some sentences in languages where they were comfortable speaking. These sentences were phonetically balanced, meaning they contained a good representation of all possible phonemes. And then there was a list of phonemes that we asked them to utter, so we could also measure the directivity of said phonemes. We did this for 37 participants in total, for a range of languages, with the most popular being French, given that we are in France, followed by English, and then a couple of speakers for the other languages. The advantage of using these microphones is that it permits us to have this high resolution array, meaning we capture everything at the same time at a resolution of 2 degrees. So that's horizontal 2 degrees, which is higher than anyone has done in the literature before. Now, I'd like to show a quick comparison with some other work that's measured voice directivity. So going from the left to the right, we have an increase in the spatial resolution of the measurements. To the left, we have measurements from Christoph from 2021. Then as we advance, we have Chuan Warnock and then Leishman and colleagues' work. For all of these data, it was captured for running speech, albeit in different languages. And what we see is that for most of the frequency bands, in this case octave bands, we see similar results. However, as we get to the area of 4K, so that's the orange here, we do see a bit of noise starting to creep in, which is a limitation of the system that we used. Now, let's look. Before we look, worth considering that these patterns here are using interpolation, whereas here we're plotting all of the points because we have the capability to do so by having a microphone every 2 degrees. Okay, before we look at more polar patterns, I'd just like to talk about the SNR in the system. We're looking here at the results for French speakers, so our largest population group. We see what we would typically expect. So we have 3 plotted microphones, that being front in blue, back in black, and pink for microphone to the side. And of course, we have higher energy at the frontal microphone, with the voice being more directional towards the front. But as we go towards the back, we have less signal due to the voice being more directional towards the front. And this resulted in some potential SNR issues at those frequencies. Now to do this, I implemented an SNR threshold of 10 dB, which is quite conservative. It means that we're not plotting data where the noise can have a significant contribution. All right, so for a first look, we're comparing running speech for French speakers. We're comparing men and women. So we had 18 male subjects and 9 female subjects. We see in blue the results for the male subjects, and we see in red the results for the female ones. And what we see is quite similar directivity patterns. And what we've done is for the points with poor SNR, we haven't actually plotted results, so we can't actually have reliable results there. It is worth noting that these results are averaged across all of the participants, so it could be of interest to look at specific subjects, differences across subjects for these groups. If we now compare our participant group that spoke both French and English, we plot the running speech directivities, and we see that they are almost or basically identical, which suggests that for these two languages, there was no difference in the directivity. Now, so here we have some conclusions of what we've just seen. For the two questions that we asked, we did not see a significant impact of the condition tested. So we didn't see large differences for the results of male versus female directivity, neither for the same group of participants speaking two different languages. However, we did measure a lot of material, and that is currently being analyzed. So that is definitely some future work to do. But also going back to the high resolution of the dataset, that could actually allow us to tackle other issues or other questions, such as, for example, is it necessary to have this fine resolution? This we will be able to see once we've analyzed all the data. And of course, it's not the same looking at averaged running speech than it is looking at specific phonemes. Finally, for this spatial sampling question, we could use the data to apply it for both objective and subjective evaluations. So that's been the first study. We're now going to look at the second one, where we're concerned with the rendering of the directivity in reverberant conditions. So in the first study, we've tried to characterize the directivity of this person. What we're interested in now is how does that directivity interact with the room, and how can we apply it or render it in a perceptually meaningful way. This is of interest, and we see due to parametric approaches which have inspired this work. So again, some work from Christoph and his colleagues looked at taking a sparse dataset, or in this case a single impulse response, and applying processing to be able to change the listener position as well as the listener orientation. In a similar manner, what we would like to do is take an existing impulse response and then modify it so that we can change the source directivity. That would be of great interest because applying source directivity can be complicated for the reverberant part, as well as just having access to the directivity for each configuration can be quite complicated. Therefore, knowing how to do it properly could save a lot of time and be useful for these kinds of applications. Now, here what we're concerned with is not actually developing a method, but actually asking how the temporal resolution of the processing impacts the final result. So we know that applying directivity in the direct sound is fairly straightforward. You have a directivity pattern and you apply it to the direct sound region. However, once you start looking into the reverberant part, the salient reflections, and even the late tail, it's quite more complicated because it depends on the configuration. And you need to start making assumptions about times of arrivals and directions of arrivals of different reflections. Therefore, the question that I was asking here is how much can we generalize the processing, so not having to look at specific reflections, while still having the same perceptual impact. And this is what we have in the research question here. So to do this, I developed a method to project directivity from an impulse response to another one. We start with an impulse response measured with a non-directional source, so a source that radiates equally across all directions. We split it into its three main regions, the direct sound, the earlies, and the late reverberation. And then we apply individual per channel, because these are binaural, and per octave band gain adjustments. With the detail that for the early reflections, we can actually control how precise or how minute. We could control the resolution of the processing for this region. We would expect that applying a finer resolution would result in a better result, and that applying more generalized processing would result in a result that is further from what we're looking for. In the end, what we get is a binaural room impulse response that has the directivity of a directional source. A quick word on what's happening for each of those adjustments. So in order to have a precise projection, we actually use reference measurements. So that means we already have what we're looking for. And what we do is for every region where we're applying this processing, we compare our input on our target, and then we apply processing so that our input matches our target. And that's what we get here. So to give us an example of how this works, we start on the left side with our impulse response measured with the omnidirectional source. Then we apply the processing, and then we get the two impulse responses that should resemble the target. And what I'm highlighting here is we have two different results. So here we have our minimum resolution, meaning we've used a big window on the early reflections, so it's less precise. And here we have our biggest time window, our smallest and therefore highest resolution time window. And what we see is that if we look at the reflections happening at 10 and 20 milliseconds in each impulse response, well, we see that the result of the higher resolution yields a more similar time energy distribution than our low resolution result. Now this is what we would expect. Here's another way of looking at it. So what I've plotted here is the interaural level difference as a function of time. So we have time on the y-axis and orientation of the source on the x-axis. And the colors represent the ILDs, with it being negative in blue and positive in red. On the top row, we have our reference impulse response, and I've plotted this ILD for some octave bands. If we look specifically at 16K, what we see is that our high resolution projection in the second row has a more similar pattern than what we see when we apply our generalized mixing time condition processing in this condition. So already we see some indication that a higher resolution yields a better result, but what we care about is it perceivable? And so for this, I prepared a listening test where we tested several different parameter values for this time resolution condition. This was tested in 3 different rooms, one of them being this one, and then we had a smaller office room and then a large lecture theater. And so using impulse responses generated with this projection method, I generated auralizations made with 2 different types of stimuli. In these auralizations, the source was completing a full turn, therefore a useful use case for directivity implementation. And I tested 7 different conditions in a mushroom test, so no visual stimuli, only the auralizations. Now, the 7 conditions were the actual reference impulse responses that were measured in each room, and then the projected BRIRs for a range of time resolution values ranging from 1.25 milliseconds all the way to the mixing time. And finally, I included an anchor where there was no directivity in the reverberant part. This is what the test looked like. We had our participant wearing headphones and taking the test in a laptop with our familiar Mushra scale, so they could play the reference and then each condition and note how similar each of the auralizations was to the reference in terms of the sound color and the spatial variations, 2 terms which were defined to participants, so they knew what to listen for. And so we had an approximate third split of novice, experienced, and expert listeners. If we look at some results, here we're looking at the impact of the directivity projection condition, as well as the stimulus on the final results. So the reason for choosing two different stimuli, one being a clap and one being speech, was that the clap is, of course, more revealing of the potential acoustical differences, whereas the speech is more like what we would use this kind of method for. And indeed, we see that the clap produced a more statistically significant difference when compared to the speech. However, when aggregated across all of the conditions and stimuli, all of the projection conditions were still different from the reference condition. So participants could tell which one was the reference. Now, if we look at the impact of the room on the results, we actually see that the room had an impact. For the small and for the medium room, we see a similar result to what we saw in the previous slide. Although in the medium room with the speech condition, we see that these conditions are statistically similar to this one, which means that the auralisation produced more plausible experiences. Whereas in the large room, we do see an impact of the projection resolution. Notably, the mixing time condition is worse than all of the other ones, probably due to the more complex behavior in such a room. So to conclude on this study, we saw that the largest window size, so the mixing time condition, was better than having no projection at all, which points towards the fact that having directivity in the reverberant part is of course important for realistic directivity projection. However, how important the temporal resolution parameter was depended on the room. And also, for one of the tested scenarios, we did get some rendering that was comparable to the reference we were comparing against. Now, in terms of what should be done next, some further steps, well, of course, it would be of interest to have a method that works without using reference impulse responses, and there's a few ways that that could be done. But also, it would be interesting to test the limits of this blockwise projection in other kinds of conditions and actually establish at what point and using which kinds of parameters could we know what that limit is. Okay, that was the second study. We're now going to go on to the third one, in which we're looking at the perception of directivity in a scenario where the virtual source is visible. So in this case, what we're interested in is how the rendering of this person's directivity contributes to how realistic the scene seems in this kind of situation where actually they are visible. A second part of the study is actually, can we predict using parameters which parameters do more closely correlate to this the perception of the naturalness of the scene. So of course, as we discussed before, including directivity in our renderings produces more realistic renderings. And there's some work that's being done by some of Brian's former students, as well as Blau and colleagues, to give an example, where including directivity in these kinds of scenarios which have a visual context produce more plausible results. So in this case, we have a post-mass experiment in a cave where we had these two actors on a theater, on a virtual theater, and including directivity in the rendering of their voices made the scene feel more plausible. However, the one thing that has not been looked at yet is how different implementations of the directivity, or how the degradation of this directivity contributes to how natural this seems. So in a way, we're trying to apply conceptually a study like what we saw in study 2 to a more similar case to the end application of this work. And so this is essentially what the main research question of this study is. How does degrading the accuracy of the directivity affect the perceived naturalness when we have an actual scene with a rotating visible talker? And secondly, if we look at some physical or objective parameters, can we actually use them to predict the impact of such degradation on how this scene is perceived? So to do this, I ran an experiment in virtual reality, simulating a case similar to what the case we've been referring to during the presentation. So in this case, this is a virtual version of this room where you have a person, in this case me, who's talking to you, and this person may turn around. And as such, the directivity of the voice is rendered in these reverberant conditions. And so what I did was I made participants judge 4 different implementations of the directivity in terms of how natural the scene felt when using each of those 4 conditions. This was done with a 7-point Likert scale, going from very unnatural to very natural. And this was done for 2 positions in the room, one being in the center and one being close to this wall here on the side. Here are the 4 conditions that were tested. So firstly, using reference measurements, so the measurements that were captured in this room, which means they are physically the most accurate, even though they were captured with a loudspeaker. So there's a question we discussed about directivity of a loudspeaker versus directivity of the voice. But in essence, this was the most realistic condition. And then we had 3 conditions where the precision of the directivity was degraded. In the first one, the static condition, where we had directivity for the direct sound, as we can see here in the full line, but actually the reverberant part was left static, meaning that as the source turned, the directivity of the reverberant part did not change. Then as an anchor condition, we had a fully static version where no matter where the source was facing, the directivity was always the same. So there was actually no acoustical change. And finally, in order to test if it's the precision or the accuracy of the rendering or the actual fact that something is changing that matters, we tested a condition where the direct sound was had the correct directivity, but the reverberant part was actually dynamic but wrong, corresponding to the source facing 180 degrees away. So if the source turned towards the right, the reverberation would change as if they were facing towards the left. If we look at the results of the experiment, we have our 4 acoustic conditions and the ratings from the participants on the y-axis. And we do see a perceived degradation of the naturalness with each condition. I've plotted the results for each of the 2 positions, which reveals the interesting result that the inverted condition was rated better in the center position than in the wall. And this is most likely due to the fact that the wall position results in more clear binaural cues when compared to the center position, which is more diffuse, and therefore the rendering is less correct, let's say, in the wall condition here than for the center condition. Now, a second step was to actually take these results and take a physical analysis of the impulse responses that were tested and try to see if we could use the objective analyses to predict these results and therefore see which of the parameters correlated best with what the participants rate. So I looked at 3 different parameters, the first of them being the direct-to-reverberant ratio. Here we see how the direct-to-reverberant ratio changes across the 4 conditions. And we do see some differences between the real condition and the direct and the inverted condition, with the biggest differences being, of course, when compared to the anchor Here we see how the interaural level differences change as a function of the source orientation. So in the real condition, we see that the source turns towards the left, and so we see an ILD. And as it turns towards the other side, we see an ILD towards the other side. In the direct condition, we see that there's a smaller change, suggesting that it's actually the reflections that contribute mostly to this ILD. In the static condition, well, nothing's changing, so we see that the values stay always the same. And in the inverted condition, we see the opposite pattern when compared to the real condition, due to the reverberation being inverted. Finally, we look at the interaural cross correlation. Again, calculated as a function of the source orientation, and we do see some changes across the four conditions, which we then used to try and predict participant responses. So what was done here is these changes in parameters as a function of source orientation were put into a linear mixed effects model. It was tested sequentially, and in the end, a model containing all of the parameters was fitted to potentially to capture which effects were most significant. And so the result of this modeling exercise was that the changes in DRR and ILD as a function of source orientation were the most reliable predictors of the participant results, while the impact of the IACC was weaker. However, the explanatory power of the model was low. We see a marginal R squared of 0.17, which is a bit higher than when considering the random effects. But actually including the stimulus as a factor plus the 2- and 3-way interactions resulted in a better fit, at least for the conditional R squared, which suggests that indeed the random effects had a significant contribution, and that the remaining explanatory power was likely due to other factors such as per participant impact. So as a basic conclusion from this study, the perceived naturalness for this visible virtual talker was impacted by the directivity condition that was used, with the most realistic rendering producing the most natural results. However, and as we saw from the different results, from different ratings at the wall and center position, again, the configuration can have an impact on this salience. Then from the tested parameters, the DRR and the ILD correlated best with the ratings, while the impact of IACC was smaller. Now, a clear future extension of this work would be to test more, do a more, let's say, complicated test where we take a method such as the directivity projection and then test how those different directivity implementations impact the final result, the naturalness of the scene, as a way to to combine those two studies, given that the 4 conditions tested in this experiment were quite basic. Okay, and with that being said, we're now on to the final study, where we don't look at directivity anymore. In this case, what we're concerned with is the acoustics at the end of each of our users. So going back to our scenario, we have our local user in a physical room with the virtual rendering of the person that they're talking to. They are in 2 different spaces, which means that physically they are each in different acoustics. And so what I'm interested in is, if their acoustics are different, may that have an impact on their interaction? Now, why do I ask this? Well, as we've said, when rendering a virtual source in mixed reality, we're going to want to render the source as if they were in the same acoustic space. But in this case, we have 2 different physical spaces. So there's a lot of literature on the impact of room acoustics on speech production, starting, let's say, with the work of Black back in the 50s, where we saw that, where he suggested that the room acoustics can actually have an impact on how on the intensity of our speech, as well as on the rate of our speech. To give an example here, we have work from Pellegrin Garcia and colleagues, where we see that as a function of the room and the distance to the target that is being spoken to, the sound level of the speech actually varies differently, suggesting that the room acoustics has an impact on this speech sound level. It is worth noting that most of these studies that have investigated the impact of room acoustics on speech use tasks that involve reading and projecting the voice to an audience, such as how I'm doing right now with you, as opposed to holding a conversation. And so the takeaway from this slide is that the acoustics of a room can have an impact on how we speak. And so therefore, we have two people in two different physical locations, but who are maintaining a conversation thanks to this mixed reality scene. Well, if their speech production is different, is the speech production of the virtual talker going to seem strange or unnatural in the acoustics that are being rendered locally? In other words, would a mismatch between the room acoustics affect how the conversation is happening? So to give an extreme example, I could be in a room such as this one, where the acoustics are quite favorable for speech, but my person I'm talking to could be in a space that is not so favorable. They may speak a bit quieter, or they may speak a bit lower. And so I may perceive them as behaving a bit weirdly, and this could eventually impact our conversational dynamics. So to test this, I ran an experiment where I set up a one-on-one teleconferencing setup across two studios in our lab, where participants saw each other and heard each other, thanks to a screen and microphones, and as well as a real-time auralisation system using a procedural reverb. And so they were asked to hold conversations, but across each trial, the acoustics could change. And so there were some points where they were in the same room acoustics, and there were some points where they were in different room acoustics. But for each of them, the conversation was always happening in their own acoustic. And so with this, we could test if the acoustics being mismatched had an impact in how they conversed or not. All right, here are the three conditions that were tested. Going from A to C, they were less favorable for conversation. First, a dry condition that was quite favorable for conversation. Then one called reverberant that was reminiscent of, let's say, a church. And finally, an extreme condition where the clarity was lower and the reverberation time was highest. That was quite unfavorable for conversation. So for each of the trials, participants were asked to have a conversation, and what would change would be where each of them would be in terms of the acoustics. So sometimes they would both be in the favorable acoustic condition. Sometimes one would be in the favorable one, and one in the least favorable one. And so having three different conditions, well, we tested out possible combinations, resulting in 9 test trials, preceded by 2 training ones. But again, important to note that for the participants, the conversation was always happening in the same space. So if I was in the favorable space and my interlocutor was in the non-favorable space, they sounded to me as if they were in my space, the favorable one. At the end of each trial, the participants were asked to rate how the conversation happened in their view, with 2 questions. Firstly, how easy they felt it was to follow the conversation. And secondly, how easy they felt it was for their interlocutor to follow the conversation, using a 7-point Likert scale. And then they could leave any comments if they wanted. So the experiment was done with 10 participant pairs, which gave us the following results. So here what we look at, first, before looking at subjective results, I evaluated the acoustic conditions. I evaluated the recorded speech from their conversations to see if the acoustic conditions had an impact on how they were actually talking. And so a number of different parameters were calculated, but the only one that had significant results was speech level. So what we see here is that in acoustic A, which was the most favorable one, participants on average spoke with a higher intensity when compared to the other two acoustic conditions as a function of their own acoustic condition. So that's in blue. Whereas in red, the impact of the interlocutor's acoustic, we see that there was no effect at all. Now, if we look at how the participants perceived the conversations, well, we see on the left the impact of their own acoustic condition on how they rated the conversation for them and for the interlocutor. We see very similar results, whereas the acoustic of their interlocutor had no impact at all. If we look at a mismatch condition, we see that there was no impact of the acoustics across each end being matched or not. So to conclude on this preliminary study, we did see that the system had somewhat of an effect on how the participants were producing their voice. However, these did not match the findings from the literature. So for example, speech rate was not significant, which is something that's being observed in the literature. However, a thing worth noting was that the task was different. So in this case, we're evaluating the speech in a conversation task, not in a reading task, as is done in the literature, which could also have an impact on how the speech is produced, because it is inherently a different kind of task to hold a conversation with someone, to be thinking about what you're saying, as opposed to just reading a piece of paper. The main result was that the own acoustic condition is what dictated how the participants rated the conditions, whereas the acoustics of the interlocutor, as well as the mismatch or not condition, had no impact. Now, it would be of interest to further work on this study or this experiment. First, by testing if the acoustic conditions that are tested in the study produce the same results as those observed in the literature when doing the same task of projecting or reading sentences, as well as testing more configurations and scenarios which are increasingly complex. Okay, so that was the fourth study. To conclude briefly, during my work these last 3 years, I've conducted 4 studies that probe room acoustics applied to mixed realities at different levels of how applied the studies are. So voice directivity measurements, projecting directivity into an existing impulse response, how the implementation of directivity affect the perceived naturalness when the source is visible, and finally how the mismatch between two interlocutors in a mixed reality conversation could impact the conversational dynamics. Each study produced some findings, although there is still some work to be done, notably in the voice directivity measurements, but each of them revealed different parts of what needs to be done for the interactions to be realistic in mixed reality. Now here I list briefly the publications that have come out of this thesis. So there's a journal article, a few conference papers, and one article that's currently in progress. With that being said, thank you very much for everyone's attention.